in this episode we're going to tackle the audio section of the syllabus. So that is on page 44 of the 2008 Stage 6 syllabus. So audio is super important. It's probably more important than the visuals in terms of the professionalism of your overall video, but it's something that every student tends to forget. So the reason why your Year 9 or 10 horror movie was bad is because the audio didn't work, okay? The reason why your Year 12 project doesn't sound professional, or doesn't feel professional, is because of the audio, okay? You can't leave it to the last minute. You've got to think of your audio the entire way through. I've seen bad major projects that were totally savable through the use of good music and sound and all things like that. Okay, so we're going to talk about audio. We're going to try and keep it to 20 to half an hour, but it is a huge section of filmmaking, animation, and multimedia in general, and it's something that you really can't discount. So there are three main groups of audio files. You've got uncompressed, lossless compression, and lossy compression. So just like images. So these usually correspond with the file size per second of audio. They will impact the quality and the size of your final file. So when you take an audio sample, if it's uncompressed, everything that was there when you sampled it is present in the final file. And that includes things that human ears can't hear. Lossy compression uses selective filtering, so we take a sort of wavelength that we've decided that humans cannot hear above and below, so higher than humans can hear and lower than humans can hear, and we cut out that information, and that helps us to work out where it goes from. And then lossless compression compresses it down, but you can get back to that original size again. Okay, so uncompressed files, WAV files, lossless files, WMAs, and then lossy compression, MP3s, or yeah, MP3 is the main one you need to know about. Okay, so when we're talking audio file size, it's very similar to the calculations for image file size. So what you need is your sample rate, and that's in kilohertz, times your sample size, so that's the bit rate of your sample, times the amount of sound you have, so how many seconds it goes for, times the channels of audio. And that'll give you the amount in bits. Then you do your conversions to do it to bytes, megabytes, gigabytes, etc. Okay? So we're going to talk about sample rate and sample size later on, but that is the formula that you want to use if you get asked for a sound size question. Now in the HSC, I'm pretty sure they usually give you the formula for sound, but it's really good to know ahead of time the way that it works. Okay. So one thing that you might want to talk about first off is field recordings. So field recordings are background sound that you don't necessarily have dialogue in or anything important. But what it does is it gives you atmosphere. So yes, it's not music. It might be just the sound of an air conditioner or a heater going in the background of a room, the sound of electric lights or a fridge. And what that does is it creates a sense of familiarity with the human environment. So we never have silence, ever. So if you're quiet in a room, you'll still pick up all of these kind of sounds from the environment. If you've ever filmed outside and listened back to your audio, you'll notice that there's a deafening amount of birds at all times. You might get wind sounds, you might get the sound of a car going past a block away. The microphone picks up everything and it's all very obvious. And the reason why we don't notice that in real life is because our brains selectively filter it out. So right now, when I'm talking in this room, I had to turn the heater off before because the heater was actually making a sound that was being picked up by the microphone, and it was really loud. It was annoying. But you don't notice it normally. Now, how does that come over and become relevant for multimedia? Well, when you listen to a file that just has the pure playback of audio, it can sound really disconcerting, especially in a film. So if you ever watch an old film from like the 1940s or whatever, around that period, they didn't put in atmospheric sound at that point. And sometimes it's just really, really quiet. So you'll have a character walk across a room and nothing will happen, and then their voice will come out, and it can kind of seem a little bit strange. most amateur film recordings by high school students don't have that background sound. So you can call field recording phonography. So we work with that. So field recording, you capture your sound and then we go back from there and we can make things sound good. So that's something that you might want to think about including. Okay, I'm going to talk about the types of microphones. Now this isn't specifically in your syllabus as well, as far as I can tell, well at least not at this section on page 44, but we'll go through it. So you've got a lapel microphone, so a lavalier microphone. It's one that clips to your body or, well, like a piece of clothing. It's very good at just taking close-up audio. We usually have a little furry thing on top of that to stop wind getting through, and plosives. So plosives are P's and S's. It's like your P and your S that you'll pick up in your normal pattern of speaking. It's really important that you don't get these when you're recording sound because it can really make things sound horrible. So a lot of that can happen from getting close to the microphone. So if I get close to this microphone, not because it can clip out and sound horrible, it will pick up the P's in my sound, and it can be really annoying. You want to try and avoid that. So another type of microphone that you might have seen used before is a shotgun microphone. Now a shotgun microphone is a really long, thin microphone that really has a pattern that just takes sound data from the end of the microphone, so only what you point it at. So a conventional microphone might have what's called an omnidirectional pattern, and an omnidirectional pattern will take in sound from all directions around it. If you have a shotgun microphone, it is often really in one direction. So that is very useful because it'll block out everything from the side. So what's that? That's great if you're filming something. So for example, if you put something on top of a camera, a microphone that is shotgun in design, it will just get the sound from what you point the camera at and not things from the side. Why is that helpful? It'll get rid of all of those sort of bird sounds to an extent that are behind you and all around you, and it'll just take the audio from where you're pointed. That's good for some things. We see them used a lot in filming. We see them a lot in news. You might see, if you've ever seen a news team filming or a sitcom or something, you'll have a guy holding up a giant boom pole with a big boom mic on top. So that boom mic is a shotgun mic. It's usually got a furry thing on it. Now we call that furry thing a dead cat. It's a great name. So what the dead cat does is it stops the wind blowing through from getting into the microphone, which will give you horrible sound if you ever film outside. So let's talk about the cameras and microphones. They suck, okay? So a camera is not designed to capture good audio. You really want to put your own microphone on top of it. So there's lots of companies. An Australian company is Red Microphones. They create a microphone that's based to sit on top of the camera. It'll sound better, it's got filtering on it, all that sort of stuff, okay? The microphone that you've probably heard of most is a dynamic microphone. So a dynamic microphone is a standard microphone. If you've ever been up on stage or seen a singer, chances are they were using a dynamic microphone. If you've ever done karaoke, pretty much 99% you were using a dynamic microphone. So a dynamic microphone has a cardioid pattern. Now a cardioid pattern kind of looks, I don't know, like a little bit like a spade or like a butt, all right? And the idea behind it is that there is some filtering on the direction of the microphone. So you will get, a cardioid mic captures everything in front of it and tries to block everything else out. So if you've got one of those sort of karaoke mics, you might notice it only really works if you sing down the top of the microphone. So you've got the ball, if you sing down there. If you try to sing into the side of the microphone, it won't pick it up. Now, why would that be important? Because when you're on stage, you don't want crowd noise, you don't want amplifier noise, so like a guitar amplifier or drums coming in and picking up through the microphone. If you've ever been in an audience and you know that like microphone screeches, so what that can be is it's called a feedback loop. So the sound goes into the microphone, it goes into the amplifier or PA system, that voice, and then it just repeats around and around and you get those feedback loops. Those are bad, we don't want those, okay? So if you've got the correct pattern for your microphone, so the right polar pattern, so to speak, that's what it's called, then you can really get rid of a lot of things like that. So a dynamic microphone is really good because it can take a beating. So you can basically yell into a dynamic microphone and it's not going to break. Now the other types of microphones are a little bit more fragile, and you can destroy them if you get too much sound going into them. So that's a dynamic microphone. Good thing about them, they don't have to be powered. If we move on to another type of microphone, so this is a condenser microphone. This is an NT1000, and thank you to Rode for supplying that for me. So they have a thin diaphragm, it's called. So a diaphragm sits on a metal backplate. So sound pressure, when that comes in, when we get sound pressure on this microphone, it pushes it and changes the audio signal. So it uses capacitance, which is a electrical term that we don't really need to know about. So sound quality and fidelity are improved. So these are perfect for precision recording and really high quality sound, okay? But you need power. You need what's called phantom power. So that's 48 volts, which goes into the microphone and it allows the microphone to actually function. So this is problematic if you're somewhere that doesn't have access to 48 volt power, which you can, just get through a standard battery pack if you really need it. But what I've got down here is I've got an audio interface, and that audio interface is supplying 48 volts of power. So you can use some batteries for it. I don't know, something that you need to think about. So this microphone is omnidirectional. So it will take sound from the back here and it'll take sound from the front here, but it won't take sound in from the sides here. Now I don't need any sound from the back here, but it is what it is. So I may pick up some room sound or something like that. But we can capture 2 or more instruments with this microphone. So for example, if we have 2 people singing into either side of this, it will pick them both up equally. If we have drums in one corner of the room and guitar in one corner of the room, and we only have one microphone, we could put this microphone in between or at varying distances from them, and we could actually get a good approximation of what it sounds like to be in the center of the room. However, if we had instruments off to this side, because it's blocked out, you won't pick up that sound. So maybe we could put the producer over here pressing buttons, and you wouldn't pick those up as clearly as you would here. If I turn the microphone sideways, it won't pick up my voice very well because the polar pattern, once again, is not working properly for them. The final microphone that I want to talk about is a ribbon microphone. Now, a ribbon microphone is a vintage design. It comes from, early radio days. So it lets you pick up the velocity of air, not just air displacement, so the movement of air. So you can actually pick up, it's very sensitive. It captures higher notes without harshness, so it's kind of warm. It's kind of got that vintage tone that a lot of people seem to really like. That said, the old ones aren't sturdy at all. You can yell into a ribbon microphone and you can tear the little piece of, I believe it's gold foil, that that is what vibrates back and forward to capture the sound. You can put 48 volt phantom power into an old one and basically just blow it up. So that's the problem with it, all right? But that said, they've gotten a lot better. I've got some ribbon microphones now that are really nice and can actually take phantom power without breaking. We're fixing all of these sort of things in time, but realistically, it's more a professional end thing. For what we're talking about here, you're probably better off just working with your old, what are we talking about? Your old dynamic microphones and your condenser microphones, but they're all good for different things. A shotgun microphone is usually a type of condenser microphone, I'm pretty sure. Well, okay, it really depends. You can have ones that are dynamic or you can have ones that are condensers, but they can pick up over a longer range, and they have, they really help to just get stuff in different angles. Okay, so we've talked about that for a really long time. I think we need to maybe split this up into 2 different files, 2 different videos. So we're going to talk about sound waves now. So a sound wave is basically just a variation in in air, basically. So it's a vibration of air that causes a sound. Okay, so an analog one varies in amplitude, frequency, or both, whereas a digital is a series of pulses with 2 states. So you got your on and off again. You've got your binary, that sort of idea. So digital signals can carry more information than analog signals, and they maintain their quality better over long distances. But when we're talking about analog sound, that's the kind of stuff that comes out of your speakers or in your voice or any sound that you make. So when we're talking about amplitude and wavelength, it can often help to think about actual waves of water coming in at the beach. So amplitude is the height of the wave. So that's how big the sound wave is. So there's a peak and a trough. The peak is where it goes to its highest point. The trough is the lowest point it goes down. So you go peak, trough, and then the wavelength is how many times it vibrates per second. So think about it, the amplitude, if we're talking about the beach, is how high those waves are. So if they're just small waves or if they're very big waves, and the wavelength is how often those waves hit the shore. Okay, so what does that mean in terms of sound? Okay, so the wavelength is the pitch of the sound, basically. The slower the wavelength, the deeper the sound. The faster the wavelength, the higher pitch the sound. So you've got lots of waves crashing on the beach really close together. You've got a high-pitched sound. You've got barely any waves crashing on the beach. You've got a lower-pitched sound. Now, amplitude, the height of the wave, that can be affected by volume. So and that can cause clipping and things like that. And yeah, let's move on. We've talked about those patterns here. So when we're talking about modulation, then we start talking about FM radio and AM radio. So FM is frequency modulated and AM is amplitude modulated. And now you know. So basically FM works better than AM in terms of sound quality. AM works better, I think, over longer distances. Anyway, not in the syllabus, don't need to talk about it. But so we know what we can take away from this is analog modulation. You can have lots of different amplitudes and lots of different frequencies. When you've got digital sound waves, it's basically on and off, okay? So you'll get a what's known as a square wave. So on, off, rather than a smooth change in time, okay? So they're both useful for certain things, okay? The two big advantages of digital technology and digital sound waves is the recording doesn't degrade over time. So over distance and time, your analog wave will degrade. If you're using a digital one, it either can be read or it can't. So no matter how old a digital waveform is, it's always going to read the same. So effectively, when we record an analog wave, it's recorded in its original form. So let's use a record. So a vinyl record works when it's read back by actually, it cuts a groove in vinyl, and when the needle runs across that vinyl, it generates an analog wave which is amplified and then it goes out there. So what's actually recorded is every analog part of that wave. When we listen to a CD, you take a number of samples every second. So you might take 44,000 samples per second. So what that does is the second is broken down into 44,000 different little chunks. And then we get a pitch at that 44,000 times per second. So it might be like, at this 44 thousandths of a second, we're making and then at this 44 thousandths of a second, it's going and then as it plays back, you'll get that over time as the wave is converted from a digital file back to an analog file when it comes out of your speaker. So the things to remember from this: analog data is continuous variable points. Okay, that's audio. Digital data is sound that's been digitized by a computer. It's converted back into audio via a sound card. So the sound card is a digital to analog and analog to digital converter. So all analog sound that comes in cannot be read by a computer unless it's changed to digital. So we change it to ones and zeros. When we want to play it back, it goes out to the speaker. So it's converted to analog information again. So that's the way that we kind of need to think about it. It's a DA, digital analog, and then, we go analog to digital when we record sound. When we play back sound, we go from digital back to analog. And that's the way that it works. All right, so let's talk about mono, stereo, and surround sound. Okay, so mono is one speaker. So we don't really use mono speakers a lot anymore because stereo sounds better. We've got two ears. It's just better if things come out from two sources around us. It's the way we hear. In the 50s and before that, we usually used to use mono sound for stuff just because speakers were expensive. Most people had one speaker. All right, if you listen back to mono recordings of stuff, the same thing comes out every speaker. So the easiest way to think about it is if you were to have two earbud headphones. So let's say, I don't know, AirPods. You know how there's no wire connecting them? So you could put one in your ear, give one to a friend. If the sound was mono, you would both be hearing the exact same sound coming out of each earphone. Now, this isn't the case for most audio recordings. Most of those are stereo, so they take they take two samples, okay? So one that's left and one's right. Even though we've only got one chord coming out of this microphone, it's actually taking a stereo recording right now. One from the left, one from the right. Now, they're probably going to be very close together, but they may not be. If I had a stereo microphone which had two capsules that were pointing in different directions, I could get a good stereo image from one microphone. Anyway, so what we do with stereo sound is we can map different parts of the recording to different speakers, headphones are speakers, they're just really tiny speakers. So what we could do is we could say, I want the drums to only come out of the left speakers and I want the guitar to just come out of the right speakers. When we listen to it back then, it gives us a stereo image of the room. So it's almost like we're in the room and we can feel the guitars are playing on that side and the drums are playing on the other one. But if we go back to our analogy before with the AirPods, if I'm wearing the right one, I only hear the guitar and I wouldn't hear the drums, and that can be a little bit strange. When we see something else is we have surround sound. So surround sound is when you have multiple speakers set up. So you might have Dolby 5.1. So Dolby 5.1 has 5 speakers, 1 subwoofer, and that's the way that we work it out. So what happens then is if something's got Dolby, and some movies do, is the sound, what the sound designer will actually decide which parts come out of which speaker, and it can create a more immersive thing for the viewer to watch. Okay, so that's how mono, stereo, and surround sound work. Now, we've already talked about converting analog to digital sound and the way that that works, but let's talk about sampling, because sampling is really important when we're working out the quality of the sound and the way that it works. So the sampling is a method that we use to digitize sound. So it's capturing audio. It's pretty much the same thing. So we take our original waveform and we sample it at various points of it playing back. So we take our analog waveform and we digitize it. Now, the more sample points we take per second, the better the quality of audio will be at the end. So if we sampled something over 10 points a second, then there would be more variation in the pitch and modulation of my voice, so we would get more of that in the final file. If we sampled it 6 times per second, you would get a lower quality file, and if we sampled it at 2 points per second, it would be even lower. Now, the size of the file obviously increases with the more samples that you make. And we don't usually do like 10 points a second. We do, 44,000 times per second if we want good value. Okay. So obviously, and as I've said before, analog doesn't work with a computer. It needs to be converted and it needs to be sampled at regular intervals. So every time we sample, it takes the pitch and it turns it into a number for the computer. And this is the sample rate. Okay. It's sampled, the higher the sample rate, the more times per second. This is called successive approximation, okay? Because it's not the exact sound of the original wave. We never keep all of our information. We do an approximation. Just like when we take a JPEG image or a picture, we're doing an approximate color level down to the amount of colors in our bit depth. Okay, so once the sound has been sampled, changed into ones and zeros, binary, etc., it can be stored in the computer's memory. So when we take that data, it very rapidly, so 44,000 times per second, runs it through the computer's sound chip. So this then makes the speaker vibrate, creates sound waves, and then it gives a representation of the sound to be played back. Now remember, it's not the original sound that's being played back. It's an approximation of that sound. So we've got all of this data, and we've got all of these samples and slices of certain pitches that are played back. Okay, so that is our sample size. But we've also then got, we've also then got the actual sample size. So we've got our sample rate, then our sample size. So sample size is like bit depth, in that we can change the quality of each sample based on how much data we want to put into it. So when we've got hertz, we can say, so a telephone works at 8,000 hertz, a walkie-talkie, a wireless microphone, we've got adequate for human speech with 8,000 hertz. Right up to 44,100 hertz, which is an audio CD. We've got, we can go up to 48,000 now, which is for DVD, films, TV, sort of stuff like that. So high quality sound, okay. Now, let's go back to our sample size. So we sample something per second, but now the bit rate, the sample size, is the amount of bits of data that are encoded per second of the file. The higher the bit rate, the bigger the file, the better quality your audio. And usually we do a bit rate of 8 or 16 bits, and so that's going to give you the best quality sound. So you might do 44,100 hertz with a 16-bit quality, and you'll have some really nice like DVD quality audio there. So bringing it back then to our audio file size, we go sample rate times sample size times time in seconds times the amount of channels. So your sample rate in hertz, so 44.1 kilohertz times 16-bit sample times 2 minutes of time times stereo channels would be 44,100 times 16 times 120 times 2, which gives you 344,000 bits. We then convert it to bytes by dividing by 8. Then we divide it by 1024 to give us megabytes, which will give us the sound in megabytes, sound value in megabytes. Okay, finally, and I know this is running long, we have to talk about, we've already talked about the relationship to file size and file compression. We've talked about throwing data out, lossless compression, uncompressed, but let's talk about some actual audio formats. So when we're talking about WAV files, WAV files are uncompressed. It stands for Waveform Audio File Format. And this was created by Microsoft and IBM, and it is a file format standard for storing on PC. It's pretty large in size, and it decreased in popularity when people started file sharing audio on the internet because people didn't really care about the quality. They just wanted to download it. At the time when these files became popular, the internet streaming speed wasn't very good. The download speed was even worse. So people were happy to take on lower quality files, and they were happy to make it work. Okay, so with that came MP3s. So MP3s are an MPEG-1 audio layer 3. That's what it stands for. And it was originally a patented digital file. And what it does is it uses lossy data compression. So what it does is it says humans can't hear above this point and below this point. We're going to wipe out all that information and just leave us with a waveform in the middle. Now that waveform might be clipped and it might sound bad. And the higher the compression ratio, the worse it'll sound. It's still a pretty good representation of sound, and most people can't tell the difference, but some people can. Some people, and I think it's hard to say that something's low quality if it's an MP3, but often if you listen through really good speakers to an MP3 and then you listen to a WAV format, you should be able to tell the difference between it if all your hearing is intact and you're not starting to go deaf. We've also got WMAs, which is Windows Media Audio, and that's an audio file developed by Microsoft. It compresses audio data without a loss of audio fidelity. So that's the idea. It's lossless. The idea is it makes it smaller, but you still have a really high quality sound. And I think that's okay. We've got an example of each there. So if you're going for uncompressed, you probably want to go with a WAV file. Lossless, you want to go with a WMA, and lossy, an MP3. I've got one more thing to talk about this lesson, and I know it's going long, but this is the only time we talk about sound. I want to talk about MIDI. Now, MIDI is different than other sound files because it's not strictly a sample-based audio file like MP3 or WAV. In fact, it's not a sound file at all. What it is it's an instruction file for sound modules on your computer that tells, or any computer or sound device that tells it what to play. So MIDI stands for Musical Instrument Digital Interface, and it works because it's a protocol that lets electronic musical instruments communicate with each other and synchronize with each other. So it transfers messages such as pitch and even the intensity of the key that you press down if it's a keyboard, and you can control the sound that comes out of that. So it's basically standard throughout the music industry. Most to all communication is done through MIDI. You've got some other things like CV for control voltage, but MIDI is the big one. So it doesn't record waveforms. It's very small because it's just sending these values instead of samples of sound. So it's not sold, and it just works when you plug stuff in. It was invented in 1983 for a single musician to control multiple devices at once. When you press down a button on your keyboard, the MIDI data comes out, which goes into whatever sound module you have. You might have a computer that's connected to it, and it tells the instrument what to play. So MIDI isn't music, and MIDI doesn't contain any actual sounds. It's just data or a set of instructions. So when you can do a lot of stuff with MIDI, but the most things is you've got a note-on signal. So when you press down a key, press a button, whatever it is, it tells a sound to start playing. Now that sound can be whatever you want. It can be a sample that you've made. It can be a digital instrument like a guitar or a piano. It just tells what note to play, when to start it. You also have a note-off signal, which is like the note stopped being played now. You can do polyphonic key pressure, so it shows how hard a key was pressed. So then you get volume, so you get that certain, like I've got a really heavy note pressed down or just a small one. You've got control change as well, so maybe a foot pedal's been put down, a pitch wheel, a slider, something like that. You can do lots of stuff with it. So when you record using MIDI, you don't actually record sound. You record instructions, okay? So later on, you can actually change what instrument that MIDI data is being put into, and it will completely change the sound. So you could start off with one type of piano, switch to another piano later on. No problems. You don't have to re-record it. You can even set it up to play as a guitar now, and it will do that, okay? But it doesn't just have to be keyboards. Any synthesizer can work with it. So a synthesizer we think of as a keyboard, but it's merely something that creates or synthesizes sound. So you can put MIDI data files into a karaoke machine, for example, and then the karaoke machine will play that information. But it might sound good, it might sound terrible. We don't know. It really depends on the sound synthesizing chips within that device. You can speed up the tempo of a MIDI file without warping the pitch, because remember, it's just a set of instructions. So we say start playing this note now and playing this note now. Now we can smush those together and speed it up, and it won't change the pitch because it's still the same instructions. They're really small. So a minute of compressed audio can be about 10 megabytes in size. A minute of MIDI is 10 kilobytes, so it's 1,000th of the size. So a lot of older video games use MIDI data. They use the sound chip that was actually in the console, so inside the Super Nintendo or the Game Boy or whatever, and then they use the MIDI to play back through that information. So that's something that you might think about if you ever wanted to decrease the size of your sound. You can use MIDI. There is a difference though. MIDI, for example, is really bad at doing voice unless you're playing samples of captured voice. Yeah, so that's, I mean, like, we've run long today, but I've done everything that we need to do in the syllabus about sound. If you have any questions, feel free to get in contact with me and I'll try and help you out. But we've talked about sound files, uncompressed, compressed, microphones, and everything today. And thank you very much.